Hi everyone. In today's episode, we're going to see how we can train our model so it can learn how to drive the car. So when it comes to machine learning, there are actually different techniques to choose from. In my case, I'm using reinforcement learning. With this approach, we don't actually know what the output should be for each input. However, we know what is best to do, like reaching the finish line and having a faster run. We know also what the model should avoid, like going outside the track and slowly driving to the finish line. So we translate these informations into rewards and penalties. Then we can evaluate the agent performance with a score or a fitness. The higher this fitness score is, the better and the more performant the agent is. Now, after giving a score to the agent, we need a way to make it evolve and learn from what it was doing during its last race. To do so, we'll use a technique called genetic algorithm, which is inspired from nature and simulates the concepts of natural selection and genetics. To start, let's have a look at our car's brain. That neural network has many weights and biases as we saw in the previous video. We can consider that as the genome of that particular car. Basically, what values are defined in that neural network describes the behavior of the car on the track. For the genetic algorithm, we need to initialize a population with n citizens that have random genes. We can refer to this population as the first generation or generation 0. It's normal to expect a huge mess when running the simulation on this generation, given the random genes. After sending these cars to the track and getting back the results of each citizen, we give each citizen some score based on its performance. Then we will create the next generation by making the citizens reproduce with each other. When picking the parents, there are so many techniques. In my case, I calculate the sum of fitnesses, then I pick a random number between 0 and s. After that, we need to iterate over the citizens and keep adding fitnesses. When the partial sum is above the random number picked earlier, we select the parent. We repeat the same process to select the second parent. Next thing to do is to cross over genes to have a new creature that shares some traits from parent A and some others from parent B. Again, there are many crossover techniques. As for me, I'm using a uniform crossover. Basically, we treat each gene separately. Each time, we pick a random number to decide whether that gene should be included or not in the offspring. We can have a 50-50 chance to pick a gene over another, or we can have some bias to privilege genes from the fittest parent, for example. Keep in mind that this process doesn't automatically mean that the child will have a better fitness than its parents. Another aspect we introduce here is mutation. Upon crossover, we can tweak the chromosomes based on a low probability. This helps with discovering new solutions. We keep repeating this process until having enough citizens for the next generation. As we previously said, this approach doesn't guarantee that we will have better offsprings. This means that we may lose our best citizens. As a solution for this, we decide to make our fittest car survive for another generation. This is also known as elitism. Next thing to do is to send this new generation to the track, and we keep repeating this until finding a solution to the problem. So let me summarize. In order to apply a genetic algorithm evolution, we have to generate a genetic representation of a solution, evaluate the solution through a fitness function, create a selection function, crossover solutions, and mutate solutions. Now let's have a look at the code. We start with creating a population of a given size. We initialize a history array as well, so we can save the best runs from each generation. Next thing to do will be to train our generation each frame. We iterate over all items and call the update method we saw before, then we render each item afterwards. When all citizens or smart car objects are dead, we will have to classify them using a fitness function. Fitness will be calculated as follows. I'll multiply the car score, which stands for the number of the checkpoints the car has reached, by 100. If the car reaches the finish line, I'll add a reward of 500 points. If the car goes outside the track, however, I'll give it a penalty of 1 minute. The fitness will be equal to the total point gathered divided by the time factor. This way, cars that reach finish line will have a greater score than cars who don't. Also, cars who reach the finish line faster will have a greater score. Next thing to do will be to evolve the generation based on the process we have described earlier in this video. We first apply the elitism to carry the fittest car to the next generation. We then select two random parents and apply a crossover to generate a new car. At the end of the loop, we increment the generation index and we replace the current items with the new ones, and we're ready to train our next generation. Let's now have a look on how to cross over cars. So each car will inherit the origin and heading of one of its parents. Given that these values are the same across all citizens, getting them from parent A or parent B doesn't matter. We need, however, to cross over the brain or the neural network of the car, since we said that the brain will be the genome of our cars. I'm also calculating a mixing ratio based on the two parents' fitnesses. This way, if the parent A performs better than parent B, the child will have more chance to inherit traits from parent A than from parent B. In order to cross over the brain, we will simply iterate over all weights and biases vectors and call a function called crossover matrices. This function will take care of this process. So the function will iterate over all the elements of the matrix A and pick a random value. If this value is below the mixing ratio, the gene will be the value from matrix B. Last thing to do is to pick another random value, and if it is above the mutation rate, the gene value will be shifted a little bit so we can discover new solutions. With this, we managed to implement the genetic algorithm. In the next episode, we'll see the evolution in action. Thank you for watching and see you next time.